In this paper, we propose a novel learnable anchored and signed distance function representation for single-view garment reconstruction, which enriches 3D position features of query points by anchor points around 3D surfaces. With Anchor UDF, we establish a unified shape learning framework to reconstruct 3D garment from a single image. Our method can handle non-closed garment surfaces, capture multiple topologies of different garment categories while retaining fine-scale geometric details. Before introducing our method, we first simply review implicit surface representation, which we use for 3D reconstruction. Compared to voxel, point and mesh representations, implicit functions, such as signed distance fields, define a surface as a level set of a function, which can represent 3D surfaces at arbitrary resolution and produce fine-scale detailed surfaces in a memory-efficient way, and have been successfully applied to single-view human reconstruction. To represent shapes with open surfaces, we adopt unsigned distance fields which assign a non-negative scalar value to a spatial point. In contrast to signed distance fields which divide the 3D space into inside and outside the surface, UDFs allow to naturally represent open surfaces. We can project the spatial point onto the surface by moving it along the negative gradient. Our proposed Anchor UDF employs both local image features and 3D position features of query points to predict UDF values. The key idea is to leverage a set of anchor points located around 3D surfaces to compute relative position features for query points, which makes the distance function better fit the garment topologies. Given an input image, a fully convolutional image encoder is first used to compute a feature map of the input image. For a 3D query point P, we project it onto its corresponding position on the image plane to compute its local image features from the feature map by bilinear interpolation at the projected pixel coordinates. In order to compute more discriminative 3D position features. For the query point P, the set of anchor points located around the surface is used to encode the 3D position of the query point. To obtain a set of anchor points which can adequately cover the surface only using a small number of points, we cluster points sampled from the ground truth surface with k-means and use clustering centers as targets to learn a regression network on top of the backbone to predict the anchor points. We then discretize the anchor points to a voxel grid and feed the grid into a point encoder consisting of a series of 3D convolutional layers to produce a 3D feature tensor of the anchor points. By applying trilinear interpolation to the feature tensor according to the 3D coordinates of query point P, we can extract the position features of the query point. Compared to using an absolute depth value to provide the 3D position information, such as PIFU, our position features reflect relative position relationship between query and anchor points, and provide stronger 3D space context to make UDF better capture multiple topologies. At last, we concatenate the local image features, the 3D position features, and the 3D coordinates of the query point as the input of a decoder to predict UDF values. Here the decoder is parameterized by multi-layer perceptrons with ReLU in its last layer. Compared to the full shape, these few anchor points, typically a few hundred, are easier to estimate. Therefore, our method can also be regarded as a course-defined strategy. A shape profile is first predicted, then further refined to produce the detailed surface. To learn Anchor UDF for an input image, we generate training examples by sampling points near its corresponding surface and computing their ground truth UDF values. Then, we minimize the L1 loss between the predicted and ground truth UDF values. A small value delta is used to clamp the maximal regressed distance to concentrate the model capacity on details in the vicinity of the surface. In order to learn the anchor point predictor, we consider a loss defined by the chamfer distance between the predicted anchor points and the targets because the set of anchor points is unordered. However, only optimizing the pointwise distance loss LUDF cannot guarantee a good estimation for the true gradient directions of UDF. For example, consider 2 points P1 and P2 on the neighborhood of a point P0, here the ground truth UDF values of P1 and P2 are close. Because the distance loss does not penalize the relationship between points, even if the loss is small, it is also possible that the predicted UDF value of P1 is larger than the one of P2. In this case, the predicted gradient direction at P0, the blue arrow, will be significantly different from the ground truth one, the red arrow. Therefore, during training we explicitly constrain the spatial gradient of anchor UDF to align its direction with the true gradient direction like this. Here the ground truth direction can be computed according to the point closest to P on the surface. Finally, the overall objective function is like this. Here lambda1 and lambda2 are loss weights. Our method can also incorporate the HD module to further improve the reconstruction performance. Here a 3D embedding extracted from the decoder of anchor UDF and local image features of high-resolution input are fed simultaneously into the decoder of the HD module to predict UDF. In our experiments, we first investigate the impact of the number of anchor points. Table 1 lists chamfer and P2S errors obtained by using 100, 300, 600 and 900 anchor points. It can be seen that using more anchor points achieves better results because stronger space context can be referenced by query points. However, when the point number exceeds a certain value, for example 900, the performance degrades. The reason is that too many points to regress increases the difficulty of learning the point prediction network and reduces its stability when testing, which further affects the subsequent shape reconstruction. This figure shows that compared to 100 anchor points, using 600 points produces finer shapes, especially for the side view. We further assess the importance of the proposed anchored 3D position features by applying different 3D position features to our reconstruction framework, including the depth value, 3D point coordinates, and our anchor point-based position features. As reported in Table 2, our position feature obtains the best results on both two datasets. The depth value and 3D coordinates only provide absolute and local position information of query points, which is not enough to predict UDF with good neighborhood consistency. In contrast, anchor points located around the surface provide the information about shape profile, which enables relative position computation between query points and the surface for more global and discriminative position features. This figure illustrates some qualitative results. Our anchor point-based position features can better recover surfaces, especially along the depth direction of input images. The depth value fails to project some points which are far away from the surface, and 3D point coordinates perform a little better, but still cannot obtain accurate surfaces at edges of the shapes. To evaluate the influence of the proposed gradient direction alignment, Table 3 reports the results with and without LGDA. It can be observed that optimizing LGDA further reduces chamfer and P2S errors. This figure shows some visual comparisons. By explicitly aligning spatial gradient direction of the distance field during training, we can obtain sharper geometric details for the visible region, such as the first row, and less artifacts for the self-occluded region, such as the second row. Next, we compare our method against single-view 3D reconstruction methods with different shape representations, including BCNet, Pixel 2 Mesh and PIFU. As listed in Table 4, our anchor UDF obtains the lowest reconstruction errors on both two datasets. This figure qualitatively compares our method with BCNet, which represents garment shapes using template meshes on MGN dataset. Although such template-based method can recover garment shapes with open surfaces, it tends to produce overly smooth surfaces and loses lots of geometric details. This figure presents visual comparison on DeepVision 3D dataset. Pixel 2 Mesh, a mesh-based method whose shape is initialized from an ellipsoid, only recovers coarse shapes and cannot handle large deformations of garments. PIFU using implicit function representation is able to generate detailed surfaces. However, it can only reconstruct closed surfaces, thus has difficulty handling garment reconstruction with multiple open boundaries. In contrast, our method can not only retain fine-scale geometric details, but but also faithfully capture open garment surfaces. We further incorporate the HD module introduced in PI-FU-HD into our Anchor UDF to evaluate the scalability of our method on high-resolution input images. To make a fairer comparison, we try to directly use UDF as the implicit functions in PI-FU and PI-FU-HD, so that they can also represent open surfaces. Table 5 shows quantitative comparison on Deep Fashion 3D. We can see that by taking high-resolution images as input, Anchor UDF HD effectively reduces the reconstruction errors, especially P2S, indicating more accurate shape details are recovered. PI-FU-HD UDF performs better than PI-FU UDF, but still worse than our Anchor UDF, which shows that direct combination with UDF cannot work well and further confirms the necessity of the proposed components in Anchor UDF. In this figure, we can see that Anchor UDF HD reconstructs more accurate shapes and richer details. Note that although PI-FU-HD UDF uses 3D embedding provided by the course level as the input of distance function instead of the depth value, it still cannot project points appropriately onto the surface. We visualize more reconstruction results of our method on Deep Fashion 3D dataset. As one can see, our method can faithfully recover detailed surfaces for inputs with various views and infer plausible shapes for self-occluded regions. Thank you for listening.